Japan, late 1943. The fog drifts low over a secluded airfield at Yokosuka. The scent of burned oil lingers in the air as a group of uniformed engineers gather around a massive wooden crate just unloaded from a transport truck. Inside lies something they have never seen before. Sleek, silver, and wounded. The American P-38 Lightning. Its twin booms stretch like the bones of a captured beast. The Japanese officers speak in hushed tones, their gloved hands brushing over the metal surface that still bears the scars of Pacific skies. Bullet holes trace its final moments, but beneath the twisted frame, the men see something else, a mystery of engineering unlike anything in their arsenal. As the crate is opened wider, one engineer leans in close, running a finger along a line of polished tubing connected to a small turbine. His brow tightens. This was no ordinary fighter. It was something far ahead of its time. And before the night ends, Japan's top engineers will realize this machine could rewrite everything they thought they knew about American aviation. By 1943, the skies over the Pacific had become a brutal proving ground. A contest not just of pilots, but of nations' technological limits. Japan's early victories had been built on agility, daring, and the legendary Mitsubishi A6M-0, a lightweight fighter unmatched in maneuverability. But as the war dragged on, a silent transformation was happening in American skies. From California's Lockheed factory emerged a new breed of aircraft, fast, heavy, and unorthodox. It was the P-38 Lightning, a twin-engine, twin-boom fighter that seemed to defy the very design logic of the day. To Japanese airmen who first faced it, the silhouette was alien. Two engines, a central pod, a flash of silver that streaked through the sun. When the P-38 first appeared over the Solomon Islands and New Guinea in late 1942, Japanese pilots were stunned. It climbed where their Zeros gasped for air. It dove without shuddering. It could strike from beyond the reach of their guns and vanish before they could react. Reports filtered back to Tokyo describing an American fighter that fought at altitudes where engines should choke. Commanders dismissed it as exaggeration, but the losses told another story. The truth was simple but devastating. Japan's aircraft industry had reached a ceiling. Its radial engines, air-cooled and simple, were ideal for island warfare, but powerless against the new generation of American supercharged engines. The Allies were mastering high-altitude performance, metallurgy, and turbo-supercharger technology, innovations that Japan's limited industrial capacity struggled to match. By early 1943, Japanese intelligence units were desperate for answers. How could the Americans field a fighter with such range, speed, and stability? How did its engines breathe at heights that suffocated every Japanese plane? Rumors spread through engineering circles about a secret air pump, a device that forced oxygen into the engine at altitude. Then, one day, the rumor became tangible. Off the coast of Papua New Guinea, a P-38 went down. The wreckage, remarkably intact, was recovered by Japanese forces. It was a gift from fate, a chance to look directly into the mechanical heart of the enemy. Engineers from the Imperial Japanese Army Air Technical Research Institute and the Nakajima Aircraft Company were ordered to examine it piece by piece. The operation was classified under top secrecy. Weeks later, under the gray morning light of Yokosuka, the dismantling began. The team expected to find good craftsmanship, perhaps advanced materials, but nothing beyond comprehension. What they were about to uncover, however, would leave even Japan's finest minds speechless. The captured P-38 had come from the skies near Papua New Guinea, one of the most contested battle zones of the Pacific. The aircraft, piloted by Lieutenant Richard Bong's squadron mate from the 39th Seahydinth 9th Fighter Squadron, had been forced down after engine trouble and enemy fire. To the Japanese ground troops who discovered it, The strange, twin-tailed machine seemed almost alien. It was too intact to be scrap, too valuable to destroy. Orders went out immediately. Recover it, no matter the cost. Piece by piece, the Lightning was crated, hoisted onto transport ships, and carried north to Japan. Its destination, the Imperial Japanese Army Aeronautical Technical Research Institute, a top-secret facility where the nation's most brilliant engineers and aeronautical officers dissected captured Allied weapons. Here, under guard and secrecy, the Americans' most advanced fighter would face its final inspection. When the crates arrived in Yokosuka, engineers from Nakajima, Kawasaki, and Mitsubishi were summoned. These were not ordinary technicians. They were the minds behind Japan's most famous fighters, men who had designed the Zero, the Kai-43 Oscar, and the upcoming Kai-84 Hayate. They had seen British and American aircraft before, but nothing like this. The P-38's twin Allison V-1710 engines immediately caught their attention. Each unit was compact yet powerful, feeding twin counter-rotating propellers. But what truly puzzled them was what lay behind the engines. A maze of tubing, turbines, and wastegates leading toward the tail booms. It was there, they realized, that the Americans had hidden the secret. The aircraft's turbo-supercharger system, a concept known to Japanese engineers but never mastered, was astonishing in its complexity. Exhaust gases from the engines were routed through long pipes to the tail, spinning turbines that compressed incoming air before feeding it back to the carburetors. It meant the P-38 could retain full power even at 30,000 feet, an altitude at which Japanese fighters struggled for breath. In those moments, as they traced the airflow with their fingers and studied the precision of the welds, a quiet unease spread through the group. The metallurgy was flawless. The aluminum was heat-treated and lightweight, yet strong enough to endure extreme pressure. Every component had been built to microscopic tolerances. They realized this wasn't just a fighter. It was a symbol of an industrial system that Japan could not match. The Americans were not improvising. They were engineering on an entirely different scale. Reports from the study would later note that the P-38 embodied the full integration of mechanical, science, and industry. It was not that Japan lacked intelligence. It lacked the factories, the alloys, and the precision machinery to replicate such innovation. Still, the engineers continued. They sketched every pipe, every valve, every rivet. They believed that somewhere within this machine lay a secret they could adapt, a clue to closing the technological gap before it was too late. But the more they uncovered, the more impossible it seemed. Inside the dim hangar of the Research Institute, the air smelled of oil and cold metal. Floodlights hung low, casting hard shadows across the disassembled body of the captured P-38 Lightning. Japanese engineers stood shoulder to shoulder, sketching, measuring, and debating in low voices. What began as curiosity had turned into astonishment. Every inch of the American fighter seemed to reveal a new kind of logic. Its construction was not built for simplicity or minimal weight, as in Japanese aircraft. It was built for endurance, reliability, and precision. The fuselage structure used advanced aluminum alloys like 24ST Alclad, layered for strength and corrosion resistance. The Japanese engineers noted how even the smallest access panels were fitted with perfect alignment, requiring no hand filing or adjustment. Proof of a manufacturing process guided by machines. Not manual craftsmanship, but the greatest revelation lay within the engines. The twin Allison V-1710 power plants were already impressive, producing over 1,400 horsepower each. Yet it was their pairing with General Electric's B-13 turbo-superchargers that left the observers speechless. These units, nestled in the tail booms, were miniature miracles of thermodynamics, designed to spin at over 20,000 revolutions per minute, harnessing exhaust gases to feed compressed air back into the engines. It was, in effect, power recycled. One engineer recorded in his notebook that the system's efficiency defied belief. The precision machining of turbine blades, the heat-resistant steel alloys, and the complexity of the wastegate control system were all far beyond Japan's wartime capabilities. Their factories simply could not produce components with such consistency or operate at such high tolerances. The P-38's electrical system was another marvel. Dual generators, a network of relays, and automatic load-balancing circuits gave it a redundancy unheard of in Japanese fighters. Even if one system failed, another would keep the aircraft alive. The hydraulic network, which controlled the landing gear and flaps, was equally advanced, smooth, responsive, and remarkably durable under stress. To the Japanese engineers, this wasn't just technology, it was philosophy. American design favored redundancy and industrial precision. Japanese design favored simplicity and pilot skill. The P-38 represented a different kind of warfare, one driven by industry, not instinct. When they examined the cockpit, the revelation deepened. The instrument layout was logical and pilot-friendly, with dual throttle controls, automatic mixture levers, and an early form of oxygen flow regulation for high-altitude flight. Every dial, every switch, was engineered with function first. No wasted movement, no decoration. At one point, an engineer reportedly whispered that this single fighter contained the work of 1,000 factories. It was not exaggeration. Japan's aircraft plants, scattered and limited, could never coordinate on such a scale. The P-38 Lightning wasn't merely faster. It was industrial power incarnate, a flying testament to what mass production, metallurgy, and precision tooling could achieve when directed toward war. And as the last panel came off, the Japanese team realized they were not just examining a machine, they were staring into the heart of the future. One they could see clearly, but not yet reach. As the P-38's metallic frame lay exposed under the hangar lights, the atmosphere among Japan's finest engineers shifted from excitement to quiet unease. What began as a study of enemy machinery had turned into a confrontation with industrial truth. The psychological impact was profound. Many of the engineers had come from the nation's proud aviation tradition. Men who had crafted the A6M-0, a fighter that once ruled the skies of the Pacific. For years, Japan's airmen believed in the supremacy of agility, lightness, and the pilot's instinct. But the Lightning represented a philosophy that was entirely alien, one of power through engineering, not elegance. When reports of the analysis reached high command, they were received with a mix of admiration and discomfort. Japanese intelligence officers summarized it bluntly. The enemy's aircraft are products of an industry without limitation. Those words carried weight. By 1943, Japan's wartime factories were already stretched thin by shortages of steel, copper, and precision instruments. Skilled machinists were scarce, and aluminum alloys of comparable strength simply did not exist within Japan's reach. The realization was sobering. Even if they understood every secret within this plane, they could not reproduce it. The turbo-superchargers alone required exotic, heat-resistant metals Japan could not manufacture at scale. The engineers' notebooks filled with sketches, but their tone grew resigned. "We know how it works," one wrote, "but not how to make it." This technical barrier rippled outward into strategy and morale. Fighter pilots, upon hearing of the captured aircraft's analysis, grew curious, even anxious. Many had encountered the Lightning in combat, noting its uncanny ability to appear suddenly at altitude, strike, and vanish into the clouds. Now they understood why. The P-38 could fight in thin air where Japanese engines gasped for oxygen. It could chase bombers over the Himalayas and patrol the Pacific with range far beyond any zero. For Japan's air doctrine, the implications were unsettling. Their reliance on lightweight, short-range fighters no longer fit the reality of the war. America's reach was expanding. and its planes could now escort bombers deep into the Pacific. The engineers' reports fueled urgent discussions within the Imperial General Headquarters. Japan needed a high-altitude interceptor. Fast design bureaus responded with ambitious plans. The Nakajima Ki-87, the Kawasaki Ki-94-2, and other experimental fighters equipped with turbo-superchargers of their own. But without the metallurgy, the machine tools, or the fuel quality the U.S. enjoyed, these projects remained mostly on paper or plagued by failures. In retrospect, the study of the P-38 became more than a technical exercise. It was a mirror held up to Japan's war machine, revealing the limits of its isolation and the cost of underestimating industrial warfare. The engineers had done their duty. They had uncovered the secrets of the Lightning, documented them meticulously, and presented their findings. But what they had truly discovered was something deeper: that the outcome of modern war would no longer be decided solely by bravery or strategy, but by the invisible strength of a nation's factories. By late 1943, the investigation reached its most delicate phase: the complete dismantling of the P-38's power system. The Japanese engineers had documented every inch of the aircraft. But one mystery remained unsolved: how the Lightning maintained such extraordinary power at high altitude. The moment came when the turbo-supercharger assembly was finally removed and laid across a workbench. The device was smaller than expected, roughly the size of a rice bowl, but its internal design was breathtaking. Polished turbine blades, balanced to a hair's width, spun effortlessly, even with a light breath of air. Its stainless steel housing was heat-treated to withstand temperatures over 700 degrees. The supervising engineer, Lieutenant Colonel Hideo Itokawa, later known as Japan's father of rocketry, examined it closely. He understood immediately. This was not just clever engineering. This was the product of a vast industrial system capable of mass-producing perfection. As they traced the network of pipes back through the tail booms, the picture became clear. Exhaust gases from the engines spun the turbines, compressing air that was then cooled and fed back into the carburetors. A continuous loop of power. The P-38's engines, unlike any Japanese design, could breathe the thin air at 30,000 feet as if they were flying at sea level. The realization struck the team hard. It wasn't just about speed, it was about altitude dominance. At that height, Japan's best fighters became sluggish, their engines starving. American pilots, however, could dive from the edge of the stratosphere with the sun behind them, invisible until it was too late. In the official report sent to the Imperial General Headquarters, the engineers wrote a single chilling line: "We have reached the limits of our technology." The findings were sobering, but also inspiring. The discovery triggered a wave of new experiments across Japan, efforts to build turbo-superchargers using domestic materials and improvised designs. But every test ended the same way: metal fatigue, turbine failure, or lack of precision tools. Still, they refused to stop. The Lightning had shown them what was possible. And in their laboratories, amid shortages and bombings, Japan's finest minds began a desperate race to bridge the gap. A race against time itself. In early 1944, the research sparked by the captured P-38 shifted into full motion. The Imperial Army's Aeronautical Research Institute launched secret development programs aimed at replicating the American turbo-supercharger. Engineers at Nakajima and Kawasaki began constructing prototypes, using whatever metals they could salvage: nickel steel, crude alloys, even repurposed ship components. But the results were discouraging. Each turbine they built failed after only a few minutes of operation. The heat-resistant alloys required to endure the intense exhaust temperatures simply didn't exist in Japan's wartime economy. The precision machinery needed to balance turbine blades within thousandths of a millimeter was unavailable. In one test, a turbine disintegrated mid-spin, tearing through the test cell wall. Still, the engineers persisted. Plans were drawn for advanced interceptors like the Nakajima Ki-87, the Kawasaki Ki-94-2, and even the experimental Tachikawa Ki-74. Each promised to reach the altitudes where B-29s roamed. But every blueprint carried the same flaw. Japan could design the concept, yet not manufacture the heart of it. Meanwhile, the Americans refined the Lightning further. Newer P-38J and L models with improved turbo systems and intercoolers began sweeping across the Pacific, escorting bombers from island to island. For Japanese pilots, the sky was becoming an unforgiving place. Reports from the front spoke of twin-tailed devils, diving from the clouds, cannons blazing, their engines howling with a metallic roar that no Japanese plane could match. In the laboratories back home, the engineers listened to these reports with grim fascination. The very machine they had once studied in awe was now dominating the air above them. The Lightning had moved from their workbenches to their nightmares. Yet amid the frustration, something changed within Japan's scientific community. The P-38 had awakened a realization that would outlast the war. The understanding that mastery of technology demanded more than brilliance. It demanded infrastructure, precision, and scale. It was a lesson learned too late for the empire, but one that would quietly shape Japan's post-war rebirth as a technological powerhouse. By the time Allied bombers began striking Japan's industrial centers in 1944, the dream of matching the P-38 had faded. The engineers could only look skyward, hearing the distant thunder of engines they now knew too well, the unmistakable voice of the Lightning. When the final report on the captured P-38 was completed, it was filed under the highest secrecy classification and sent to both the Imperial Japanese Army and Navy technical commands. Only a handful of officers ever saw the full document. The tone was clinical, but between the lines ran a sense of awe and defeat. The conclusion stated plainly, "This machine represents the total unity of science, production, and power. Replication under current conditions is impossible." The dismantled Lightning was kept at the Yokosuka research hangar for months. Engineers returned to it again and again, sketching the turbocharger layout, measuring alloy samples, and photographing each component. Every bolt was catalogued. But by 1944, the focus of Japan's war effort shifted. The empire was losing territory, its factories starved for aluminum, fuel, and manpower. The P-38, once a symbol of hope for catching up, became instead a silent reminder of what could not be achieved. When American bombers finally reached the home islands, Yokosuka was among their targets. In one raid, the hangar housing the P-38's remains was hit. Flames swept through the structure, melting aluminum into shapeless pools. The fragments that survived were later buried under debris. No part of the original Lightning was ever recovered. After the war, U.S. intelligence officers examined captured Japanese technical archives. Among them were the detailed schematics and analysis notes from the P-38. At investigation, they were astonished by the depth of understanding. The Japanese had fully grasped the turbo-superchargers' function, even its metallurgy. But the Americans also noted something else. The analysis ended where industrial capacity began. Japan had comprehended the science, yet lacked the tools to transform theory into production. The war had proven that genius on paper could not defeat factories that never stopped running. In the ruins of Yokosuka, a few surviving engineers quietly reflected on what they had learned. They had witnessed the edge of modern engineering and seen how the future would belong not to the boldest pilots, but to the nations that could turn precision into power. In the years that followed Japan's surrender, fragments of memory from that Yokosuka hangar resurfaced in unexpected places. Many of the same engineers who once studied the P-38 went on to rebuild Japan's post-war industry. Men like Hideo Itokawa, who had sketched the turbo-superchargers airflow system, later led Japan's early rocket programs. Others joined companies like Mitsubishi and Kawasaki, applying lessons first learned from the wreckage of the Lightning to peacetime technology. Precision machining, thermal resistance, high-efficiency turbines. They spoke of the P-38 with a kind of reverence, not as an enemy weapon but as a teacher. It had shown them what an integrated industrial system could achieve, how thousands of components, built to microscopic accuracy, could function as one living machine. For a nation rebuilding from ashes, that idea became a blueprint for the future. In declassified post-war reports, American analysts found traces of this shift. They noted how Japan's engineers, once isolated by wartime secrecy, emerged after 1945, with an acute understanding of modern manufacturing. The same curiosity that had driven them to dismantle the P-38 now fueled Japan's transformation into a technological power. Within 2 decades, the descendants of those wartime engineers were designing jetliners, high-speed trains, and engines whose precision rivaled, and sometimes surpassed, the very systems they once studied in awe. Yet the emotional shadow of that discovery lingered. To the men who had handled the Lightning's parts under wartime tension, the memory was bittersweet. The humbling moment when they realized that victory in modern warfare no longer belonged to courage or skill alone, but to production, science, and scale. The P-38 had entered their laboratories as a captured trophy and left as a quiet revelation. It taught them that the true battlefield of the 20th century was not in the skies, but in the factories that built what flew there. By the time peace returned, the wreckage was gone, melted, bombed, forgotten. But the ideas it revealed endured, shaping Japan's future long after the smoke of war had faded from the horizon. In the end, the story of Japan's encounter with the captured P-38 Lightning was not about conquest. It was about revelation. Amid the chaos of war, when every discovery was measured by its potential to kill, this one instead illuminated something deeper: the boundless reach of human ingenuity. Inside that Yokosuka hangar, surrounded by silence and steel, Japan's top engineers came face to face with the future. The Lightning was not merely a machine, it was a message. It told them that victory in the modern age would no longer hinge on bravery alone, nor even on strategy, but on the unseen symphony of science, precision, and production working in harmony. The men who once studied it in wartime secrecy would later build in peace, drawing on those lessons to transform a defeated nation into one of technological mastery. The same minds that had once whispered in awe at an American turbo-supercharger would, decades later, design bullet trains that redefined speed and efficiency, and rockets that reached the stars. The P-38 had proven that even in the most violent chapters of history, knowledge has no allegiance. It moves across borders, survives destruction, and waits to be rediscovered by those willing to learn from it. When Japan's engineers opened that crate in 1943, they thought they were examining a weapon. In truth, they were unwrapping a mirror, one that reflected the limits of their present and the possibilities of their tomorrow. And though the original Lightning was lost to flames, its legacy endured, not as a relic of war, but as a spark of understanding that helped turn defeat into innovation and silence into progress. In that sense, the captured P-38 never truly belonged to either side. It belonged to history itself, a machine that taught both the conqueror and the conquered what the future of flight would demand.